Hey, good morning. My name is Justin Barnes. I'm a sophomore MBS student, and today I'm going to give you a brief description of our flow rig. So right here, we've got a tank of water. We've got a pump that brings it up through this pipe and around, as you can see, and it'll continue on. And there's multiple devices that we can use to measure, to take and make engineering calculations. And then this right here is our orifice plate. This differential pressure transmitter shows us the difference in pressure in the water. Good luck getting this data in Excel. Learn it right now while you can. It's going to be one of your best friends whenever you get into engineering school.
So Justin showed you the flow device. And what you're going to be doing is you're going to be preparing a spreadsheet for an experiment that we're doing on this to try to see how accurate each device is. You see, the flow device actually has different ways to measure flow. It has a turbine meter, which the flow goes through here, hits a little wheel, it displays right here. That is the most accurate. We're going to use that as a standard. It has what's called an orifice plate, he pointed out. It looks at the delta pressure here and it displays it and you can calculate flow. It has what's called a rotometer right here. And then it actually has this valve that we can close where instead of flowing through here, the water flows out of this tube. So we can do a direct capture. We can capture the water, time it, and then calculate gallons per minute from that. And so that's what we want to do. So here's what's going to happen. This turbine meter is our standard, and we can set the flow by changing this little valve right here. So what we're going to do is we're going to set the flow to all these different flows right here. And we're going to set it at each flow 3 different times. So for 3 times, we're going to look at the flow measurement that's actually happening from the turbine meter. That's our standard. And then we're going to measure it from all of these other ones to give us data to then know how accurate they all are. And so from each of those other flow devices, we'll calculate error, the reading we got minus the standard from the turbine meter, and then we'll calculate percent error. Whatever that error is, the difference divided by the standard, which is the one from the turbine meter times 100. So that's what we're going to do, and so you're creating a spreadsheet to help with that. Because anytime you do some kind of engineering experiment, you're always taking data. You're always going to have a data collection sheet like this. So this is the final product, and there's usually information up at the top right here about who did it, the different things that were going on, and then there's places to record data and places to calculate things. So in this, here's the turbine flow that was recorded for all the different times. These measurements in here in the white are data points that we recorded. The yellow are equations. And so all the places through there are equations. And so what you're going to do for this particular spreadsheet is you're going to add all the equations to facilitate this. Now, if we were doing this lab, what would happen is we would come in, I've set the turbine meter, and now I would come down here to the rotometer and I would look. This shows a blow up of it. This device basically works. The water flows through here. This float right here floats based upon the properties of how the water is flowing through, and the faster the water, it floats more based on Bernoulli's principle, and then we can read that. So what we would actually do is, once that gets set to its flow rate, we would come in here and we would take 4 readings. 4 because this moves up and down some. And so you see, we would record those 4 readings. Now, one of the things I want to say is, you see, we've got all these decimal places when we're recording it. We can't read that many decimal places with these. I actually created this data to make it work with the graphs I wanted you to do. So we would not be recording the number of decimal points that you're actually going to see in the data. But we would record the readings from this, and then we would take the average of those 4 to get the flow from the rotometer at that particular flow rate from the turbine meter. So you'll add the equation to get the average. Then we're going to get the error. So the error is going to be that reading minus that. Then we're going to get the percent error, which is going to be that, the error divided by that again. So we would do it for the rotometer. We then would do the same thing. We would read the orifice plate here. What this does is there's a plate in there, and fluids theory tells us that based upon the pressure difference here, which is what this meter is reading in inches of water, we can run that through an equation and get the flow. Now, for your purposes right now, we're not even worrying about that equation, but that delta pressure and the flow is recorded for you. The only thing you really care about is this. That's just in there. You're not doing anything with it. So that's your flow. So again, you're going to calculate the error, that minus the turbine meter flow and the percent error. And then finally, we're going to come and we're going to get a bucket, and we're going to put that hose in the bucket. Then when we put it in the bucket, we'll get all ready. We'll say on your mark, get set, go. We'll put it in the bucket, and we'll start timing. We'll leave it there for a certain amount of time. We'll pull it out of the bucket. We'll take the time, and we'll record the time right here. Then what we'll do is take that bucket, and we'll weigh it and record the weight of the bucket right there. And then from that, we can come in, and we now can get the weight of the water, because it's going to be the total weight minus the weight of the dry bucket. And you see there's the dry bucket right there. So we've got to subtract the weight of the bucket out to know the weight of the water. We then can convert that into pounds using, you see this factor up here in S6 right there. We then can convert that to gallons using this factor right down here. That then tells us the capture flow. So we can take, okay, how many gallons did we capture over how much time in seconds? So you'll add the equations to calculate all that. And then just like before, we can get the error and the percent error. So you see, this is what the spreadsheet would look like if you were doing this lab when you were done. You'd have all your data, all your calculations, and you can see these graphs down here that the students added. And then they would use these in their lab reports to talk about the different things that were going on. Now, you're not going to do these graphs right now. You need to learn a little bit more about graphs before you can do some of the things in here. And I'll show that to you, but that's not the focus of this lab. These graphs are in there, so as you put your equations in and fill these in, then you'll be able to see these graphs populate. And so that'll be kind of cool that you can see it, but you're not going to do those graphs right now. You're just going to be doing the equations. So the spreadsheet that you are working on looks like this. There's one before it with the data static so you can see the numbers in there. But yours is going to look like this, so all these yellow places, you're going to go in and add equations. At the top of your spreadsheet, there's an equation for error and percent error if you forget, as well as these conversion factors. And then right here, it's just reminding you how to do that equation if you don't remember. Okay, and then also the other thing you're going to do is you're going to add these equations, and then you're also going to graph just the error for rotometer, the error for orifice plate, and the error for direct capture. So that's these three graphs down here. And again, if you look in the spreadsheet that you've got, under the static, those graphs are in here, right here, for you to go and look at. They're just pictures, so you can't actually, the graphs won't change, but they're there so you can go in and look at. And there's one more thing about graphs that I need to show you, or this graph of the direct capture is going to drive you crazy. So let me blow that up so you can see it. So if you look at this graph, when you first do the graph of the direct capture, it's going to look like this. The zero, the axis, is going to be way up here, and the numbers are going to be in the middle of the graph, and you're like, what in the world are you doing in Excel? Don't worry about it. Right-click on the right axis and say Format Axis, and then notice right down here, horizontal axis crosses. By default, it's automatic. No, I want to say a particular value, and I want the horizontal axis to cross at minus 0.12. So I'm going to say minus 0.12, and lo and behold, That moves down there, and now everybody's happy. So what you're going to want to do is go into this sheet, add the equations, and then add a graph for the rotometer error, the orifice error, and the direct capture error. And like I said, these graphs, I left them in there, so as you start to add your equations, these will populate just so you can see them. Okay, good luck, and this will just let you practice all the things that you've learned about Excel and begin to get comfortable.